You're here because you want to master periodicity with a University of Cambridge graduate. Let's begin. Now, I have to preface this. Periodicity is one of the chapters that I really hate. Now, that's because it is one of the chapters that you really have to memorize a lot of equations, all in one chapter. But don't worry, I'm here to help you memorize it as efficiently as possible. If you want a free copy of my notes, be sure to hit the link below so that you can download a free copy for yourself. You can use my notes to follow along my lesson closely and make your own notes in the process as well. Periodicity is all about trends that we can follow within the periodic table itself. Now, we've run through some of these trends already. For example, when we look at ionic radii or atomic radii, we always want to look at several of the factors that we've already run through before in my atomic structure masterclass. For example, you want to look at the number of shells because there's shielding effect involved. You want to look at nuclear charge, and all of this influence the effective nuclear charge. So you want to assess your effective nuclear charge before you explain why there's a difference in your ionic radii. If there's greater effective nuclear charge, that means there's a lower ionic radii, and vice versa. Next up, there's melting point trends that you need to take note of in your period 3 oxides. Now again, I must emphasize you need to memorize all this, but you actually can apply some of the concepts that you've already learned in your previous chapters to help supplement this so you don't really have to memorize everything. Well, you're just applying knowledge from your past content. Now, a general recap is from your chemical bonding lectures, you can see that your sodium oxide, your magnesium oxide, and your aluminum oxide are giant ionic lattice structures, whereas your SiO2 is a giant molecular structure and your P4O10 and SO3 are simple molecular structures. From there, you can already see that there will be differences in the melting point because there's different attractive forces between the ions or different intermolecular forces between your molecules, etc. etc. So do remember to recap on your chemical bonding concepts for this chapter. So if you look at this melting point pattern over here, you realize that over here are the giant ionic lattices, and it's to no surprise that they have very high melting points, along with SiO2 because it's a giant molecular structure. So no surprise there that it has a very high melting point. And there's also no surprise that your P4O10, your SO3, and it's not really covered well, but Cl2O7 has the lowest melting points because it has simple molecular structures. Okay. I'll just put here the giant ionic lattice as well. However, I do note a few anomalies as well. So if you look at the numbers over here, there's like 1 and there's 2. So for 1, you realize that Al2O3 has a lower melting point than MgO, which is very weird. Well, this is because your Al3 plus is a very high ionic charge. It's a higher ionic charge and a smaller ionic radius than Mg2 plus. And because of that, it has a higher charge density and it gives Al3 plus very high polarizing power. And because of this, it's able to polarize the oxide electron cloud, and it's actually because of this that it has very high covalent character, and this will weaken the ionic bonds in your Al2O3. It's still mainly ionic bonds, but it just has covalent character as well. So because of that, the ionic bonds are weaker, and therefore we know that the ionic bonds are the main or more rather the electrostatic forces of attraction are the main attractive forces that pull the Al2O3 together, and if it's weaker means lesser energy is required to overcome these electrostatic forces of attraction. Now if you look at the chart again above, you realize in anomaly number 2, your SO3 has a lower melting point than your P4O10. Well, this is because there's more electrons in your P4O10 than your SO3. We've also covered this in the chemical bonding masterclass, but remember that both of them have dispersion forces, and if there's more electrons in one of the simple molecular structures, this means there's increase in polarizability of your electron cloud, and this makes it so that there's more energy needed to overcome the stronger IDID or the dispersion forces. Now let's move on to melting point trends of your period 3 chlorides. So the general trend, if you recall from the chemical bonding masterclass, is you have to look at the structure and the bonding. So NaCl and MgCl2 are giant ionic lattices. AlCl3, SiCl4, and PCl5 are simple molecular structures. And therefore, you can see the trend in the melting points. You see that NaCl and MgCl2 have a higher melting point than the rest of them. Now, if you look over here, there's 3 anomalies that will be covered. Now if you look at anomaly number 1, it's very similar to anomaly we covered just now. We see the MgCl2 melting point is actually lower than your NaCl. And this is because Mg2 plus has a higher ionic charge than your Na plus and smaller ionic radius, and therefore has a higher charge density, higher polarizing power, and therefore your MgCl2 has a covalent character that will weaken the ionic bonds. So very similar, yeah, because this is a repeated explanation. So you just need to memorize it once, but the explanation is the same. Now for anomaly number 2, you realize that AlCl3 is actually having a very low melting point over here. And if you recall what I said just now, it's actually a simple molecular structure. Now why is that? Now that's because Al3 plus has very high ionic charge. Again, it's higher than Mg2 plus, right? And it's the same explanation over here, it's the same, but this time, because it has very high covalent character, right? It's so high that it actually makes it a covalent bond instead of an ionic bond. So therefore, it's a simple molecular structure instead. So yeah, this is a repeated explanation again and again. Now, if you look at this next anomaly number 3, you realize that PCl5 has a higher melting point than your SiCl4. Again, this is because there's more electrons in your PCl5 compared to SiCl4. So there's increase in polarizability of your electron cloud, and therefore there's more energy required to overcome the stronger ID or the dispersion forces. Again, it's a repeated explanation again and again. So you realize there's two main concepts that you have to take away from this melting point trends for your chlorides and your oxides. Next, we're going to look at acid-base reactions of your period 3 oxides. Now, if we take a look, you realize that the pH of your period 3 oxides starts very high and then goes all the way down. And this is kind of making sense as well, because if you move from the left to the right of the periodic table, you realize that we go from metal oxides to actually non-metal oxides. And we know that our metal oxides tend to be basic, whereas our non-metal oxides tend to be acidic. And those in the middle can have amphoteric properties. Now take a scene. So if we look at Na2O, we know that it dissolves completely in water, and this is the reaction. Again, please memorize all reactions, memorize all equations. They can be tested in any part of the exam paper. Now, because it dissolves completely in water, it actually produces your NaOH, and this gives it the very basic property. Right? So if you react Na2O with an acid, for example, over here, you can get your salt. MgO, on the other hand, dissolves partially in water because it has very high lattice energy, so do take note of that. So there's a reversible arrow over here, but still, it can produce your magnesium hydroxide. And of course, it can react directly with acids as well, so making it a very basic oxide as well. Now, your Al2O3, however, has no reaction. Again, this is because of even higher lattice energy of your Al2O3, so it requires more energy to break the ionic bonds. So therefore, it doesn't dissolve, but it can react directly with acids or bases because it's an amphoteric oxide, so just take note of that. So your Al2O3 can react with HCl over here, for example, to give AlCl3, or it can react with a base, so this will give it the complex ion. Next up for SiO2, SiO2 cannot really dissolve in water as well. Again, this is because there's large energy required to break your covalent bonds between the Si and O atoms in your giant molecular structure. Okay, but it can react with bases under very concentrated solutions. So for example, if concentrated NaOH, it becomes an acidic oxide, and it can give this molecule. So there's no way around it. You have to memorize this molecule, and you have to know the products of this reaction. Next, we have P4O10. So this is an acidic oxide. So it can dissolve in water, so you can form your phosphoric acid. And since it's an acidic oxide, it can also react with NaOH directly. And for the balancing of the equation, just memorize this. There's really no shortcut. Now for SO3, it's also an acidic oxide, so it dissolves in water, it gives sulfuric acid. So this is one way to memorize it, that this gives the acid, and this is the acids that you're very familiar with. And since SO3 is an acidic oxide, you can react with NaOH to form your sodium sulfate. Next up, let's have a look at acid-base reactions of your period 3 chlorides. So for NaCl, there's no hydrolysis, so it's actually neutral. But your MgCl2 undergoes slight hydrolysis over here. And you gotta know that this is what is happening, and this will be further covered in your transition metals lecture as well. But your metal over here, let's say Mg over here, will be surrounded by your water molecules over here. In actually 6 water molecules, very specific, 6 water molecules will surround your metal atom or your metal ion. Okay, and what's going to happen is with hydrolysis, so if you actually have water, it's actually going to take out a H from one of the waters over here. So this will actually give H+, giving that slight acidity to the MgCl2 when MgCl2 dissolves in water. Now if you look at AlCl3 in excess water undergoes more extensive hydrolysis than your MgCl2, so it has the same reaction over here. In excess water, it's going to be acidic, but in limited water, okay, it actually reacts vigorously with water and forms white solid and white fumes of HCl. So you can undergo either of these reactions over here. So you can see water is one of the reagents, and it can form your aluminum hydroxide or your aluminum oxide, and this will also produce HCl in the process in the background. Next, we have SiCl4. SiCl4 actually reacts vigorously with water to form white solid and white fumes of HCl. So you can form HCl very nicely, a very strong acid that comes out of it. So do take note of that, and you can form silicon dioxide as well. And your PCl5, it also reacts vigorously with water to form white solid with white fumes of HCl. So just take note. Again, these are the products of your reaction that you have to know. Now we move on to trends of your group 2 elements. So do take note that we've already covered some of the trends of your group 2 elements, like your atomic radius, your first ionization energy, your electronegativity, your melting point. These are all covered in the chemical bonding masterclass and your atomic structure masterclass. So this is where your fundamentals need to be very solid. So do refer to those lectures, or do refer to my past videos if you ever forgot any of the content. Now next up, we're going to talk about reducing power / chemical reactivity of the group 2 elements. So you realize that as we go down the group over here, going down the group leads to a decrease in the E0 value as well here. Now you may not be familiar with E0 values for now, but this is just proof of the concept. And what is the concept behind all this? Well, as we go down the group, you realize that the atomic radius actually increases, so this leads to weaker electrostatic forces of attraction between the nucleus and the valence electrons. So it's easier to lose your valence electrons in the process, and therefore it has a greater tendency to be oxidized to the ionic form. And this also means that the reducing power or the chemical reactivity will increase. Remember, if the molecule itself is more likely to be oxidized, means it has very good reducing power, because as you have reducing power, as you reduce your reducing agent, you reduce another molecule, you yourself will be oxidized. So vice versa, if you have great tendency to be oxidized, it also means that you have very good reducing power. So do take note of this very key concept. Now, if you look at the electrode potentials, this is just mainly the evidence, because as you have more negative E0, it means there's a greater tendency to be oxidized. Okay, and if you have a greater tendency to be oxidized, like I said, this means you have stronger reducing power. There's a typo over here. And therefore, it has higher chemical reactivity as well. How about the thermostability of your group 2 salts, especially with large anions? So here are a couple of examples. When you have carbonates, nitrates, or hydroxides even, and these are group 2 salts, okay, you want to look at the size and the charge of the cation, right? This is the most important. Okay, because as you go down the group, right, the size of the cation will increase, but the charge stays the same. So again, we are always looking at charge density. Now, as the charge density decreases, your electron cloud, okay, of the anion is polarized to a lesser extent. This means that the bonds in anion are weakened to a lesser extent. If the bonds are weakened to a lesser extent, it means the bonds are actually stronger, and this also means that there is higher thermal stability. Hopefully that makes sense. Now, there's also the size of your anion that also could contribute to it if, for example, the cation remains the same. So yeah, as a note over here, usually they won't test it such that the anion changes, but if they do, just know that if you have a bigger size of your anion, it will help in making it more polarizable. So if it's a bigger size, most likely the thermostability will be decreased. Now onto a small portion for group 17. For group 17, you need to know the trends of your boiling points, but we've also already covered this in the chemical bonding masterclass. Again, they're all simple molecular structures, so you just have to take note that they have dispersion forces and take note of the strength of the dispersion forces as well. They will be affected by the number of electrons. Now as for oxidizing power or the reactivity of your group 17 elements, so again, there is the same explanation that we use. So as we go down the group, we logically think that the atomic radius will increase, so there's a decrease in electrostatic forces of attraction between your nucleus and the valence electrons. So there's a decreased tendency to accept electrons, right? So if you have a decreased tendency to accept electrons, you have a decreased tendency to be reduced. Now this means that your oxidizing power will decrease. So just go step by step whenever you get lost in your explanation for this kind of behavior. As for thermostability of your HX molecules, as you go down the group, again, every time we always start with going down the group, your size of your halogen atoms will increase. This means lesser effective overlap of your orbitals. And then your bond strength of your HX will decrease, and therefore lesser energy is needed to break it, and thus your thermostability will decrease as well as you go down the group. So that's all for periodicity. Again, I must emphasize that you must go through very carefully and memorize all the reactions that are involved, especially for your period 3 chlorides and your oxides, because these will often be tested, and if you do memorize them, these are guaranteed to be free marks in the exam. Now if you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my chemistry tuition class, be sure to hit the link below so that you can book a free call with me, and I can run through any doubts and clarifications you may have, and even go through for free your past exam paper. And I will show you why my tuition class is the best fit for you. I'll see you in the next lesson.